Great. So yeah, I want to talk about a way to understand certain geometric properties of the Hilbert schemes of points via certain special bundles called tautological bundles, and we'll compile these bundles into series whose properties we want to study. So the first thing to do is talk about what the Hilbert scheme of points are. So if I start with any smooth quasi-projective variety over the complex numbers, the Hilbert schemes of points parametrizes all possible ways to equip finite point sets with scheme structure. And this Hilbert scheme of points breaks up into a bunch of components indexed by the length of the corresponding scheme. So that is, if I pick some non-negative integer n, the Hilbert scheme of endpoints on X, which I'll denote here as X upper square brackets n, parametrizes zero-dimensional subschemes of X and of length n. That is, the complex dimension of the space of sections of that subscheme is n. And this is what I'll call the Hilbert scheme of endpoints on X. So I've drawn an example down here. So this is this big blob is my scheme X, and I've marked some subscheme. So there's a few points, these kind of upper 2 points. They're just points of length 1. The support of this subscheme at these points is one-dimensional, or it's just 1, sorry. And at these other 2 points of the support, there's some kind of thickness. There's some non-reduced structure. So say this point here, I've given multiplicity 2, and that means I have to pick some way to thicken the scheme to have length 2 at this point. And here I have more choices. I have this point of multiplicity 3, and so I have some length 3 subschemes supported at this point. And the direct sum of all these subschemes gives me a subscheme whose total length is 1 plus 1 plus 2 plus 3, which is 7. And despite being pretty simple moduli spaces to describe, they turn out to be pretty complex varieties. So in general, they're highly singular. They kind of reduce structure. They can be reducible. And even when X is 3-dimensional, the dimension of the Hilbert scheme of endpoints on some threefold is not known. So they can be very, very nasty varieties. But when the dimension of my underlying subscheme or the number of points is low enough, then they're well behaved. So in particular in this talk, we'll focus on the case when the dimension of X is the most 2. So we'll look at Hilbert schemes of points on curves and really focus on Hilbert schemes of points on surfaces. But let's start with the curve case. So if C is a curve, I don't have too many choices of subschemes once I fix points and their multiplicity. That is to say, in some arbitrary variety, there's lots of ways in which to thicken a subscheme. But as I've tried to indicate in this drawing here, if I have a point, there's only one direction to thicken it. In other words, length n subschemes of C are just determined by some collection of points on the curve and some choice of multiplicity at each of these points. So a length n subscheme of C is in this collection is in one-to-one correspondence with the total space of effective divisors of the same length on C, of the sum of n points, possibly with some multiplicity. And this extends to an isomorphism of moduli spaces. So the Hilbert scheme of endpoints on C is the same thing as the symmetric product of endpoints on C, which is some smooth variety. And so these behave as nicely as could possibly be hoped. So for example, if my curve is just P1, then the Hilbert scheme of endpoints on P1, what's that? Well, all divisors of a given length on P1 are linearly equivalent. And so the Hilbert scheme of endpoints on P1 is just the total linear system associated to any one of these divisors. So I can take the projectivization of the space of global sections of O of n, and that's just n-dimensional projective space. Okay. What happens for a surface? Now the situation is slightly more complicated. So the symmetric product of endpoints on a surface is singular. There are these rational singularities. But as is the case for any Hilbert scheme, what I do have is a morphism to the symmetric product that takes a subscheme and records the support of the subscheme and the length of the subscheme at each point of the support. And that's called the Hilbert Chaumorphism. And so that's this map rho that's drawn here. And over the open locus of the symmetric product, where all points are distinct, this is just a one-to-one map. That is to say, if I have some collection of n points, so here n is 3, each with multiplicity 1, then the only possible subscheme is just the direct sum of the structure sheaf of each of these points. But if I allow these points to come together, more complicated things can happen. So for example, in this picture down here, in the symmetric product, say we have 1 point of multiplicity 2 and 1 point of multiplicity 1. Well, we have now a choice of how to thicken the subscheme supported at this point if we want to look at all possible subschemes that are of the surface that are mapped to this element of the symmetric product. And so we have to pick some subscheme of length 2 supported at this point. And we have a p1's worth of choices of thickening. So we can choose to thicken it in any direction. And as more and more points come together, these fibers get more and more complicated. So we have more and more complex choices to make about how we thicken our subschemes. So this is already more complicated than the case for curves. But somewhat miraculously, the Hilbert scheme of n points on a surface is still smooth and of dimension 2n. So that's equal to this dimension of its big open locus. And in particular, this Hilbert Chaumorphism, which takes a subscheme to its support, is a resolution of these rational singularities of the symmetric product. And this, as I mentioned already, once we increase the dimension of S beyond 2, this fails to be true once n is like 4. So it's really some kind of special fact about surfaces. Okay. And so now that we have these Hilbert schemes, I want some kind of way to understand their geometry. And with any moduli space, one nice way to try to probe the geometry of moduli spaces is to understand certain bundles, natural bundles that the moduli spaces carry and characteristic classes thereof. And so the bundles that we'll look at today are called tautological bundles. And how do these work? Well, if I start with some vector bundle, or everything I say will work just as well for K-theory classes of rank R, then I can produce a new vector bundle on the Hilbert scheme of n points on my variety called the tautological bundle. And this will be a vector bundle of R, the original rank, times n, the number of points. And so these can be described functorially by pulling back to the universal family, pulling back from my scheme to the universal family, then pushing forward to the Hilbert scheme. For today, it's kind of totally sufficient to know just what the fiber is over a given subscheme. So the fiber over some subscheme Z is the space of global sections of the vector bundle tensored with the structure sheaf of that subscheme. And so these vector bundles and their characteristic classes come up all the time. So they come up often in geometric calculations. If you want to count some kind of incidence, they come up. They come up if you want to compute, say, like secants to projective embeddings of curves. If you want to count nodal curves and surfaces, they come up in the study of strange duality. And then kind of closer to what we'll think about today is they come up in physical computations. So in certain partition functions of supersymmetric gauge theories, these bundles contribute what's called fundamental, or their duals contribute what's called anti-fundamental matter. So they show up in many different situations. And like with many structures on the Hilbert scheme, nice features emerge when we allow the underlying variety to be fixed, but the number of points to vary. So kind of famously, the Hilbert scheme of points on surfaces carry the action of a Heisenberg algebra once you consider the union over all n. And so here we'll see a kind of different incarnation of this phenomenon. So what do I want to do? I want to fix some underlying projective surface S. And then I want to fix a collection of vector bundles or K-theory classes on S. And I want to fix some integers, say non-negative integers, K1 through KL. And I'm going to form a power series given this data. And so each term of this series will be the Euler characteristic of a certain vector bundle over the Hilbert scheme of points. And what I'll do is I'll take my first vector bundle, take the tautological bundle associated with that, and then take the K1 exterior power, let's say. And then I want to do the same for the second one, the third one, take the second exterior power of the tautological bundle associated with the second one, and so on. And then I want to tensor all of these together, take the Euler characteristic, and then form these into a series. into some kind of infinite power series. And this is what I'll call the K-theoretic descendant series. And so then the question is, okay, what kind of series do I get? So in principle, this gives me some infinite series, and it turns out that so let's see some examples of this series. So the kind of simplest examples I want to consider are if I, instead of having a projective surface S, I have some curve, and I can do the same construction. So let's go back to this first example of a Hilbert scheme we saw. So I want to consider kind of no tautological bundles, just the structure sheaf, over the Hilbert scheme of endpoints on P1. And we saw that the Hilbert scheme of endpoints on P1 is just Pn. And so the structure sheaf is just O of Pn. And the Euler characteristic of O of Pn is just 1. So this series is just the sum of Q to the n, which is, I can write as 1 over 1 minus Q. It's the Laurent expansion of 1 over 1 minus Q. And note, another way to write this is kind of stupidly is 1 over 1 minus Q raised to the power of the Euler characteristic of O of P of 1 on P1. Okay, so this is kind of example -2, and the numbers will increase. So the next example will still be for curves. And we'll generalize the example of P1. So if I have some general curve, again, the Hilbert scheme of endpoints on the curve is just the symmetric product, and its structure sheaf is just the structure sheaf of the symmetric product. And by definition, or almost, the Euler characteristic of the structure sheaf of symmetric, the symmetric product of a curve is just the Sn invariance of the kind of total cohomology complex of the n-fold power of the curve itself with its structure sheaf. And then I want to take some kind of graded dimension, which records the even dimensional cohomology with a positive sign and the odd dimensional cohomology with a negative sign. But this complex is the same as an n-fold tensor product of the same complex just for the curve itself. And so what this series ends up recording is the graded dimension of a polynomial ring modeled on the graded vector space given by the cohomology of the structure sheaf of the curve. And so that graded dimension looks like symmetric functions in zeroth cohomology in the even piece tensored with odd functions in the cohomology of the, along with the exterior algebra in the odd piece. And this ends up being the following series, which I can record as 1 over 1 minus Q raised to the power of the Euler characteristic of the structure sheaf of my curve. Okay, so this is we saw something similar in the previous slide when the curve had no first cohomology, but in case it does, then you get the following. Great. Now back to surfaces. So something similar kind of applies. So what if I want to evaluate the same Euler characteristic instead of working over the Hilbert scheme of points on a curve? Now I do this more complicated Hilbert scheme of points on a surface. Well, now it was useful before to compare things to the symmetric product. And so let me do that here. And the way I do that is by this morphism, this Hilbert Chaumorphism, which we constructed, that takes a subscheme to its support with multiplicity. And I can just try naively to push the structure sheaf of the Hilbert scheme forward and see what happens. And the nth symmetric product is some quotient by a finite group, so it has rational singularities. And so therefore, the higher cohomology of this push forward vanishes. Moreover, the Hilbert Chaumorphism is proper, birational, and the symmetric power is normal. And that tells me that the push forward, its zeroth cohomology, I just recover the structure sheaf of the symmetric product itself. And so if I want to compute the Euler characteristic of this of the structure sheaf of the Hilbert scheme, that's the same as computing the Euler characteristic over the symmetric product of the structure sheaf of the symmetric product. And by the exact same argument as on the previous slide, that's 1 over 1 minus Q raised to the power of the Euler characteristic of the structure sheaf of the surface itself. So again, we see some way to express this total series, a nice way to express this total series in terms of as a rational function in terms of Euler characteristics over the underlying surface. And so this turns out to be true in general. So this is the kind of main theorem of the talk. And what do we want to do? So this is the same data. We fix the projective surface S, fix vector bundles, and fix these degrees of exterior powers we want to consider, and form this vector bundle for each n, take its Euler characteristic over the corresponding Hilbert scheme of n points, and introduce this variable q, which keeps track of the number of points, and form the following series. And the result is that the series is always a rational function of a very particular form. So it's some polynomial in Q whose degree is bounded by the total sum of the degrees of the exterior powers we're taking in the bundle. And this is divided by 1 minus Q raised to the power of chi of OS. And so if chi of OS is negative, then this is some polynomial. And if chi of OS is positive, then we get some rational function whose denominator we can control. Okay. And so let me make some remarks about this theorem. So this denominator we saw is already comes from the most simple example that we already computed, this Euler characteristic of the structure sheaf of the Hilbert scheme. Special cases of this theorem have been explicitly computed in previous work for, say, small numbers of bundles, or small degrees of exterior powers, or small ranks of these bundles, or small n. And I started by going through some examples for curves. So it's natural to ask, well, is the same thing true if I replace S by a curve? And the answer is yes. So the same kind of statement holds if I replace S by a curve C, and I replace all these vector bundles on S by vector bundles on the curve C. So that's previously known. Great. So let's see another example. This is the first positively numbered example. So if I take some rank 2 vector bundle on the surface, and I look at the sum over all n of q to the n of the Euler characteristic of the third exterior power of the associated tautological bundle over the Hilbert scheme of n points, then what do I get? Well, I get the following expression. So I get some rational function, and the denominator is 1 minus q to the chi of OS, and the numerator, as you'd expect, or from the theorem, is some polynomial of degree matching the degree of the exterior power we've taken. In this case, it's 3. And then there are some coefficients. And another kind of feature to note, which is true in general, is that the coefficients of this polynomial are themselves polynomials and natural Euler characteristics of V, of the tangent space to S, and then Schur functors thereof. So in this case, exterior powers and tensors of exterior powers. And this formula holds for any S and any V. And this is the kind of general shape that all of these series will look like. And there's a kind of result we'll see that'll show up later of Ellingsrud-Gerscher-Len that tells us that this is kind of what we'd expect. We'd expect in general that these coefficients are polynomials, but the rationality is some kind of, I should say maybe the polynomiality of the numerator is some kind of new feature that doesn't follow for free from previous work. Okay. So yeah, that's the main theorem. It's already been stated, so I can relax a little bit, and everything I say from now on is just bonus. But what's another thing you can ask? Okay, well, there are other kind of ways to extract information from bundles on varieties. Instead of looking at Euler characteristic, I can look at integrals of characteristic classes. And you can consider a cohomological analog of the same problem, and these are called cohomological descendant series. And to do that, one starts with the same data. One starts with a surface, vector bundles, and some integers. And the natural replacement for the exterior power is some kind of Chern character. And one can take the corresponding degreed component of the Chern character, and take, instead of a tensor product, just a product in cohomology. But unlike with K-theory, we have to worry about dimension concerns here. So as the dimension of Sn increases, we need some kind of class to multiply by to ensure that we're integrating a cohomology class of the appropriate degree. And so that's typically packaged in the cohomological version of the problem by including the total Chern class of the tangent bundle. And so this isn't so different from the K-theoretic series we were considering. So one can use Grove-de-Grieben-Rock to write the K-theoretic expressions in this form, only instead of having a total Chern class, one essentially has a Todd class. And just replacing that Todd class that shows up in K-theory by this total Chern class, which shows up in cohomology, one gets series that behave very differently, interestingly enough. So even in the simplest example, one doesn't have a rational function. So if I take no insertions, then I have to integrate the top Chern class of the tangent bundle, and so that's the Euler class. And when I form these into some series indexed by a variable q, what I get is the following product. So I get something that looks like up to some factor, some power of the Dedekind eta function. I get a product over all integers r of 1 over 1 minus q to the r raised to the Euler characteristic of the surface. And so this is not a rational function. And this holds more generally. You can ask, okay, maybe if I normalize by this factor, I would still have some kind of numerator that looks like a polynomial, like we did for K-theory, but that's not the case. So even in the next simplest example you could try was computed by Carlson and Okounkov. And that tells me, well, if I take the first Chern class of the tautological bundle associated to the trivial bundle on S, and I multiply it by the 2n minus first Chern class of the tangent bundle, that's the kind of appropriate Chern class to consider that will put me in the right degree. And I form all of these integrals into a series. Then the results, well, I still have some kind of same denominator as before, but the numerator is not a polynomial. So I have some piece that depends on Chern numbers of the surface and the corresponding bundles. But then I have this extra series here. So again, it's some kind of infinite series that's not a rational function. And in fact, it's a Q deformation of a zeta value, of the zeta function evaluated at 2 minus the zeta function evaluated at 3. So it's not polynomial, it's something very transcendental looking. And this is expected, I think, but not proven to be the case in general. So if I consider this general cohomological descendant series, then the expectation is this belongs to a ring of what are called Q multiple zeta values. So they're particular Q deformations of these kind of generalizations of the Riemann zeta function. So if in this sum in on the bottom right, if I just sum over one integer, I get the zeta function. And if I allow myself to sum over some kind of sectors, then I get what are called multiple zeta values. And these are expected to be deformations thereof. So this ring contains quasi-modular forms, but it's a bit bigger. And so these kind of series somehow live in the modular world, whereas the K-theoretic ones live in the world of rational functions. And like before, we can try to compare the kind of, like in K-theory, we compared the problem for surfaces and curves, and we saw we got the same behavior. In cohomology, if we formulate the same problem over a curve, then we get different behavior from the case for a surface. So again, if I pick a curve, vector bundles on the curve and some numbers, and I form this series from pieces of the Chern character of the corresponding vector bundles, and include the total Chern class of the tangent bundle to the Hilbert points on the curve to bring me up to the right dimension, then it's one of many computations done by Johnson, Operio, Pandare-Panda, that the resulting series is again the Laurent expansion of a rational function in Q. So it behaves more like these K-theoretic series we already saw. And so I put the kind of 4 series I've discussed so far into the following table. So on the top, we have the corresponding moduli space. On the left, we have the flavor of the descendant series we want to consider. And then we see the kind of behavior in the tables below. So in both cases, the K-theoretic series are expected to be rational functions. For a curve, both types of descendant series one consider rational functions, but for a surface, one gets this divergent behavior, where the Chromological series is some kind of modular Q multiple zeta value, and the K-theoretic descendant series are rational functions. And so that suggests that these are kind of interesting things to study if the behavior is so. If something about this, including this Todd class about this K-theoretic series, about combining these series in a particular way, produces a rational function. And I still don't quite understand. It would be good to have some kind of conceptual reason for this divergence in behavior. I should also say the problem this problem has also been studied for quat schemes on surfaces and quat schemes on curves in many examples. And these, unlike the Hilbert scheme, are no longer smooth, so one has to study them by means of their virtual classes, but one can formulate the analogous virtual descendant series. And in many cases, the behavior has been verified to behave much more like curves. So in all those cases, one also gets, that have been checked, one also gets rational functions. And the expectation is, in general, that virtual descendant series for quat schemes on surfaces and curves are both rational in the cohomological and K-theoretic formulations. Okay, so that's some kind of background on how this result fits into what's known about descendant series for Hilbert schemes. So what now? How do we actually? So in the remaining time, I want to talk about how to actually prove this result. So how to show this polynomiality of the K-theoretic descendant series. And so the first step will be to reduce the problem to a case where one has more techniques for computation. So this kind of first idea we tried for the structure sheaf, where we just push forward to the symmetric product and see what happens. This becomes very, very complicated once these tautological bundles start included, and we consider their tensor products and so on and so forth. Computing their push forwards is not something I think is so easy to do. So one has to have some kind of other techniques, and when S is toric, there are other techniques one can access. So let's see how to do this. So first, I want to reduce to the case when S is toric. And okay, for the following discussion, just to save us some notation, instead of considering multiple tensor products, I'm just going to consider an exterior power of a single vector bundle, and the argument works the same if I have some tensor product. So yeah, we already saw, for example, that the Euler characteristic of the third exterior power of a tautological bundle associated to a rank 2 vector bundle in the Hilbert scheme of 2 points is this kind of nice polynomial in Euler characteristics of the vector bundle and the surface itself. And this polynomial will grow in complexity as the inputs in the problem grow in complexity. So as the rank increases, or as we take bigger exterior powers, but in general, there's some kind of universal result that works for Hilbert schemes on surfaces and Hilbert schemes on curves, which implies the following. So it implies that there exists a universal polynomial that depends on, say, some number k, some number r, and some number n. And it'll be a polynomial, in this case, in 5 variables. And the polynomial is universal in the following sense. So for any s and for any v whose rank matches this r, then the Euler characteristic of the kth exterior power of the tautological bundle associated to v on the Hilbert scheme of n points is given by this polynomial evaluated at the 5 Chern numbers one can extract from the surface and the vector bundle. So the first Chern number of the surface squared, the C2 of the surface, C1 of the vector bundle squared, C2 of the vector bundle, and C1 of S integrated against C1 of the vector bundle. And if I have more vector bundles, then I have more possible Chern numbers, but the principle remains the same. And so yeah, this polynomial is the kind of important thing to take away is though this polynomial depends on the numbers in the problem, it depends on the degree of the exterior power, it depends on the rank of the vector bundle, it depends on the number of points. It does not depend on the surface and the vector bundle itself. So it's the same polynomial for any surface and any vector bundle of the given rank that we pick. And so that tells me that, so I have some polynomial. What's kind of, how do I, if I have some polynomial, how do I figure out what its coefficients are? Well, one way is by some kind of interpolation. So by evaluating the polynomial at enough points, I can figure out its coefficients. That is to say that this polynomial, PQRN, is uniquely determined if I can compute the value of this Euler characteristic for enough examples of the surface and vector bundle so that its evaluation at these points separates the possible monomials that can occur. And so there's lots of ways to generate enough surfaces and vector bundles. One of many ways to do this is to pick my surfaces to be toric. So I can just take, even it suffices to take the surface to be, say, P2 or P1, and to consider torus equivariant vector bundles on the surface. And taken together, these will give me enough examples of Chern numbers to completely determine what the polynomial is if I know its value at these Chern numbers. And so to prove some kind of general statement about the behavior of these descendant integrals, it turns out to be enough to compute them for toric S and equivariant vector bundles V. And this is a kind of this kind of reduction using these universal polynomials is a powerful technique that's used beyond Hilbert schemes. So often in studying moduli spaces of sheaves on surfaces, one tries to use some kind of wall crossing to push the problem to a regime where one is working over, say, some product of Hilbert schemes where this theorem can then also, where some kind of version of this theorem can also be applied. And so this is a very common and useful technique in any kind of that often shows up when studying the enumerative geometry of sheaves on surfaces. And then from here, there's different ways to proceed. So sometimes it's convenient to compute over K3 surfaces, while computing over toric surfaces is difficult. For this particular problem, toric surfaces seem to be better suited. Okay. So step 2, why are toric surfaces useful? Once we are working over a toric surface, we have an additional tool which is called equivariant localization. And so that lets us express the Euler characteristic for a toric surface in terms of Euler characteristics over each of its individual toric charts. So we can reduce the problem further from studying toric S to studying some equivariant version of the problem where the surface is just affine to space. And so if I have some torus acting on my toric surface with toric charts UI, then equivariant localization says that the K-theory of the Hilbert scheme of endpoints on my surface is determined by the K-theory of its torus fixed points. And in other words, the Hilbert scheme of endpoints on its surface looks I only need to study what happens in neighborhoods of each of its torus fixed points. So the restriction map from the Hilbert scheme to the disjoint union of products of Hilbert schemes on each of the toric charts is an isomorphism. So I have some map from the disjoint union of toric charts to my toric surface itself, which I've drawn here. And this induces a map going in K-theory the other way, and this restriction map turns out to be an isomorphism. So that's the kind of first useful piece. Now I only need to understand what's going on for C2. Great. And then the second piece is the following. So instead of just considering a single descendant series, it'll be convenient to combine all of these descendant series into some larger series. And so I'll introduce a new variable, which I'll call y, and I'll form this kind of genus, which I've denoted by phi, and it'll be the sum of the corresponding descendant series for each individual k, and then this variable y will keep track of k, will keep track of the degree of this symmetric power. And the advantage of this function is it's multiplicative. So that is to say the total exterior power of some vector bundle, of some direct sum of vector bundles rather, is the tensor product of the total exterior powers of the corresponding corresponding individual summands. In other words, if I have some surface that splits as a direct union of splits as a union of two different surfaces, then this genus evaluated over the surface is the product of these genera evaluated over each individual component. So I can recover the genus over the surface from knowing its behavior over each of these components. And so if I combine this fact with the fact on the previous slide that I can study Euler characteristics, that I can relate sheaves over the Hilbert scheme of points on the surface with some sheaves over Hilbert scheme of points on this disjoint union, I get the following fact. So if S is toric with these toric charts, then the genus over the toric surface is equal to the product of the individual genera over each of these copies of C2. So if my toric surface S here is P2, then it will be a product of 3 copies of the corresponding function for C2, 1 for each of these fixed points. And I take my vector bundle and just restrict it to each of these toric charts to get some vector bundle on each individual, near each individual fixed point. Okay. And so I further reduce the problem to computing this genus phi in the case when S is C2. But of course, there's a kind of important remark to make here, that we started with some projective surface and we were taking Euler characteristics over projective surface, but now C2 isn't projective. So how do we make sense of Euler characteristics over it? Cohomology groups over C2 can be infinite dimensional possibly. So it's important that each of these Euler characteristics is regarded as a T equivariant Euler characteristic. So this because we have each of these vector bundles now carries a torus action. And so each of these Euler characteristics is a character for the torus. So each of these Euler characteristics transforms with this torus T. And the Euler characteristic records the character of how so this Euler characteristic is the character of the corresponding torus representation. So for where does this live? Instead of being just some number, now each of these Euler characteristics is some rational function in the torus itself. So even though it's infinite dimensional, each individual torus weight space is finite dimensional, so I can make sense of its Euler characteristic. So even in the simplest example, this is kind of interesting. If I look at coordinates on affine 2 space and say each of the coordinate functions is scaled by T1 and T2, then the character of functions on C2 is just the character of the total space of polynomials in the coordinates. And so what do I have if I look at the total space of polynomials in 2 variables and I record their coordinate weights? I have, say, the monomial, one monomial, say x1 has weight t1, monomial x2 has weight t2, and so on. And if I look at the total character of all possible polynomials, then it can be summarized in this rational function here as 1 over 1 minus t1, 1 minus t2. This records the characters of all monomials on C2. And if I have some more complicated sheaf, then the kind of corresponding rational function will be more complicated. And so this equality of genera, where we factor this series over a toric surface as a product of contributions from each of its toric charts, should be interpreted as an equality of rational functions in T1 and T2, as the right side is some as some projective variety rather each of these Euler characteristics is not just a rational function, but a Laurent polynomial. Sorry, that shouldn't be monomial. It should say polynomial in T1 or T2. And then if I want to recover the non-equivariant version of the problem that we're initially interested in, that can just be obtained by forgetting about this torus action, that is specializing these torus parameters to be 1. So instead of recording the individual weight pieces, just recording the overall total dimension. So that is to say, what the kind of point is by passing to this problem over C2, we introduce this additional complexity of keeping track of some kind of torus action. But that will give us another tool, which we'll use later. So now that we've pushed everything to C2, we can reformulate the same theorem, but over C2 itself. And so now if I have some collection of T equivariant bundles, say W1 through WL, on affine 2 space and numbers as before, I can form the same kind of series. I take the same tautological bundle associated to each vector bundle, take the corresponding exterior power, and tensor them together, and form them to some series. And by the factorization earlier, it's sufficient to show that the series has the following form. So there's some kind of denominator, which one can think about as 1 minus 1q to the total Euler characteristic of functions on C2. And we want the numerator, again, to be some polynomial in Q whose degree is bounded above by the sums of the KIs. And now, instead of just being some polynomial with integer coefficients, it's some polynomial whose coefficients are rational functions in the equivariant variables associated to my torus T1 and T2. And so we've reduced this problem to this other problem. And how are we going to approach that? Well, there's kind of two steps. So the first is to return to this tool of equivariant localization. Again, having a torus action is very powerful. We can use that to write this series over C2 as a combinatorial sum. And that'll take the form as a sum over Young diagrams or as a sum over two-dimensional partitions. And once we have this sum, we can match it with kind of known expressions in combinatorics, and that will be with what are called Macdonald polynomials. And the resulting combinatorial expression can be controlled using a certain Macdonald polynomial duality that was due to Mellet and was deduced from results of Garcia, Heyman, and Tesler. And so the first thing we need to say is how to write this series combinatorially. And it'll look as follows. So we've already seen that localization lets us pass from some kind of scheme to its fixed points. So I want to go a little bit more in depth into that. So this is another useful theorem in equivariant K-theory. And here's its kind of simplest incarnation. If I have some torus that acts on a smooth scheme, and to simplify things, we'll assume that the fixed point set is isolated and finite, let's say, and I have some equivariant vector bundle on my smooth scheme, then I could compute the Euler characteristic of this vector bundle as some Euler characteristic over its fixed point sets. So I have some contribution coming from each of the torus fixed points. And what I do is I take my sheaf, I restrict it to the fixed point, and then I look at all polynomials in the normal directions to my fixed points. In other words, I divide let's say I multiply by polynomials in the conormal directions, in the weights of the conormal directions at that fixed point. And so what's the mnemonic to remember this kind of expression? If my M had some check cover of open neighborhoods U of P, centered at each of these fixed points P of T, then the corresponding term is the Euler characteristic of the sheaf restricted to that open neighborhood. And so this looks like I'm computing in some kind of check cover. And then the next thing you have to show, kind of mnemonically, is that the contribution of the intersections of these check covers doesn't end up contributing anything. It turns out to be torsion in equivariant K-theory. This kind of sum over each open neighborhood recovers the Euler characteristic of the sheaf over on the whole scheme itself. And when applied to the Hilbert scheme of points, each of these pieces has some kind of combinatorial description. And so I'm going to kind of not go into terrible depth about describing each of these pieces, but this first piece I think is fun and worth learning about. So the first thing I need to do is characterize the fixed points if I want to apply this theorem. And so let's suppose I have my torus action on the Hilbert scheme on C2 that induces some torus action on the Hilbert scheme, and the fixed points correspond to monomial ideals in polynomials in two variables of co-length n. So how do those look? Well, here I've drawn out all the monomials, and this kind of light blue section, suppose those are all the monomials in my ideal. If I take the leftover monomials and draw these green boxes around them, what I get is a Young diagram. I get some partition. So here I get the partition 3, 3, 1, and there this ideal. Once I take its quotient, I have 7 monomials left over, and so this is an ideal of code length 7, and it's a Young diagram of size 7. So the fixed points of the torus action of the Hilbert scheme have this very straightforward combinatorial description in terms of partitions, and this works for any for Hilbert schemes over any dimensional affine space, where instead of two-dimensional partitions, I have partitions of the appropriate dimension. So if I do this over some 18, the affine 18 space, then I get 18-dimensional partitions. The same thing works there. Okay, and so now that I've described the fixed points, I need to describe how this sheaf data looks over each of these fixed points. And that turns out to also have combinatorial descriptions in terms of these partitions. So suppose I have some just single vector bundle W, and I want to describe the restriction of the tautological bundle to a given fixed point lambda. And so again, it's convenient to introduce this variable y and sum over all these possible exterior powers. It makes the resulting expression a little bit more concise. And it turns out I thought, kind of 47 minutes into the talk would be too late to be throwing kind of a lot of intricate combinatorial expressions at everyone, but it's some explicit combinatorial expression whose degree depends on the size of the partition on n, and it's in terms of the monomials that appear in this ideal lambda. Great. And the denominator has a slightly more complicated but still combinatorial expression. So here these are polynomials in the conormal directions to the Hilbert scheme at the fixed point. And this also has some explicit combinatorial expression in terms of the arms and leg lengths of a partition. And so to each box of a partition, I can associate its arm and leg lengths, which are the number of boxes that are below or to the right of it. And from from this data, I can construct this explicit combinatorial expression. So it's something kind of complicated and not super straightforward to analyze, but it's something that can be made explicit. And so I've recorded the numerator as this product n lambda and the denominator as d lambda. And so putting each of these pieces together, we know how to characterize the fixed points. We know how to characterize the restriction of the sheaf to the fixed point. And we know how to characterize the polynomials in the conormal directions combinatorially. One can get some combinatorial expression for this whole sum over all possible n and all possible degrees of exterior powers. And it looks as follows. One gets some sum over lambda one takes a sum over all possible Young diagrams lambda. One introduces the variable q that records their length. One takes this product of n lambda, where the length of the product corresponds to the rank of my vector bundle W, and this denominator d lambda. And it turns out this series can be related by a combinatorial identity to a very similar looking series where the roles of Q and Y are interchanged. And so how does that look? So let H lambda be the Macdonald polynomials in what's called Heyman normalization. So if you've seen the Macdonald polynomials before, that's great. If you haven't, you don't need to worry too much about it for the purposes of understanding the rest of the talk. All you need to know is that there are certain homogeneous polynomials of degree lambda, of degree size of lambda. So if I have a partition of n boxes, then H lambda is some homogeneous polynomial of degree n. And the consequence of an identity of Mellet is the following duality. So on one side, we have a numerator that exactly matches this expression we have up here. So this is exactly the descendants, this equivariant descendant series for this vector bundle W. And then there's some kind of normalization factor that you don't need to worry too much about. That should remind you a little bit of these normalization of these denominators that have been showing up throughout the descendant series in the talk. And on the right-hand side, we have a similar kind of series, but with the roles of Q and Y interchanged. So on one side, this Q to the lambda has been replaced by some other homogeneous polynomial of degree lambda. These are the Macdonald polynomials. And the numerator, instead of taking some product over that corresponds to the rank of this vector bundle W, we have just a single copy. And instead of evaluating it at this variable Y, we now evaluate it at Q. And this denominator d lambda turns out to be the same. And again, on the right-hand side, there's some kind of normalization factor. And so when we want to study this series on the left here, this equality lets us relate it to some kind of similar looking series, only with the roles of Q and Y interchanged. And so it would be, there are some kind of cases in which there's a geometric way to interpret this equality, but it would be interesting for me to have some kind of geometric way to understand both sides of this equality in kind of arbitrary cases where I have arbitrarily many J, or the vector bundle W can get arbitrarily large. But in any case, why is this identity useful? Well, this was a series we wanted to study. I explained it could be written in this kind of combinatorial format here. And then we can use this identity to exchange the roles of Q and Y. So up to some kind of prefactor, it's the same kind of expression, only we take a Macdonald polynomial, evaluate it at this Y, and this numerator is evaluated at Q. And the descendant series were some kind of statement for fixed K. So suppose I wanted to compute the K cubed term of the corresponding series, then, or sorry, the Y cubed term of the corresponding series, say the K equals 3, the third exterior power, like we did in the examples earlier, then I would want to extract the Y cubed term of this series. And so if I want to study the Y cubed term of this series here, then this Y shows up in the numerator for every partition lambda. And so I need to, in principle, understand this every term of the series lambda. There's some kind of contribution coming from every term. But once I do this exchange, then down here, I mentioned these H lambda, their degree was the number of boxes that showed up in this lambda. So if I'm only interested in the Y cubed term, I only need to study these terms of this series for lambda of size at most 3. And once lambda is bigger than 3, then I know the terms are irrelevant. The terms don't contribute to controlling this series here. And so then I just get some kind of finite expression, and that finiteness of that expression translates to this corresponding polynomiality. So I have some this n lambda was also some polynomial of degree lambda, and that tells me that my Q can only have at most degree the size of lambda. And so not only does this prove the desired polynomiality, but it gives me, in principle, some closed form expression for any of these series. I mean, it can be a complicated closed form expression in terms of some combinatorics, but it's something that you could tell a computer to do for any fixed power of k, for example. And again, it would be interesting to have some kind of geometric explanation for why you can why somehow only understanding the first few terms of the series are enough to kind of determine all possible terms. If there's some geometric relation among these bundles or some kind of categorification of this result that lets you of which this combinatorial fact is a shadow. But in any case, one gets the desired polynomiality there. And so to kind of put the pieces together, we've shown that this kind of equivariant version of the theorem, that the equivariant K-theoretic descendant series are polynomials over this infinite product. And piecing that together, kind of unwinding the logic, then we recover the same result for a general projective surface, where the K-theoretic descendant series are polynomials over this denominator given by the descendant series with no insertions. And of course, these polynomials get more and more complex as these integrands get more and more complex, but we know that the answer will be some kind of polynomial. So yeah, I'm a little bit early, but I'll stop there. Thanks for your attention.